Okay, so welcome to the first lecture series lecture for this year. It's my pleasure to introduce Tom Ball. Tom is a principal researcher at Microsoft. He is also the manager of the Research and Software Engineering group there. I always think of Tom as a verification guy because I'm a verification guy and that's how I know him. But in fact, Tom comes from more of a programming languages background, programming analysis background. And it was actually just over 10 years ago, or for a little more than that, one of my friends had just joined Microsoft, and they were building up this the research group at the time. And this was Sriram Rajamani, and he was a hardware verification guy. And he was saying, oh, there's this amazing guy I'm working with, and he's so smart, and he knows all this stuff I don't know, and all this great stuff's happening. And then that's Tom. And when I met Tom, then Tom was saying, there's this incredibly smart guy that he knows all the stuff I don't know. That's Sriram. And these guys are this amazing sort of dynamic duo. They launched this SLAM project, which has really become a mainstream part of Microsoft's development process for device projects. It's required, I guess, for anything to get checked in. And it's been very influential work. And so I was looking, just last year, CAV, which is the big verification conference, gave the CAV award for this work. At the same time, PLDI, which is a big programming language conference, gave the award for basically the same paper, saying that this is the most influential paper from 10 years ago. I was just looking now, Tom actually previously won the most influential paper at PLDI for previous work. And just so you don't believe that Tom is a total has-been that did all his work more than 10 years ago, he just won I guess they call it, distinguished paper at OOPS Law? So another best paper award at OOPS Law, another programming language conference just last year. And so with that, let me find Tom and let him go ahead.
Thank you, Alan. Yeah, I've got a big, thank you. Yeah, people tell me I have a big enough head as it is. No, it's really great to be here. We've had Microsoft Research has had a lot of collaborations with Alan's team and actually with other folks, Gail Murphy and a bunch of folks at UBC. So it's great to come up here. I took the train last night and that was quite an experience. Relaxing, but not exactly quick. The work today, so when we did SLAM, we relied a lot on automated theorem proving and SAT solvers. But at that time, 10 years ago, Microsoft Research was just a consumer of that technology. We were not doing research in it. But in the last 5 to 6 years, we've had the chance to get into that with the hiring of some great people. So Leonardo Demora, Nikolai Bjorna, Margus Vianis, Ken McMillan, all work in this area of symbolic methods, essentially for verification. And today, it's my pleasure to really represent their work to you. So we build a lot on logic, not just in terms of foundations, but we build engines that reason with logic. We can call these automated theorem provers. Other people may call them decision procedures. And on top of those, we build a lot of tools for verification, for defect detection, for program testing. You can see more about that technology at this URL, which is essentially represents 30 some odd people in Redmond who work in the area of formal methods, software engineering, programming language, compilers, and runtime in general. So. Actually, Zohar Mana, he's a professor at Stanford and also the advisor of Nikolai Bjorna, has this nice quote that logic is the calculus of computer science. If you think of fundamental formalism that we use, both in theory and in practice, logic is really what comes to the fore. If we think of complexity theory, it turns out that we have a lot of complexity classes these days. Back when I was a graduate student, we had the Gary and Johnson handbook. And, if you could prove your problem was NP complete, then the idea was, wow, it was hard. And you could go to your manager in a software company and say, look, my problem is hard and all these other people have NP complete problems of which mine is in the same class. And they've been trying to make efficient algorithms and not succeeded. So that, that classic result is about satisfiability in propositional logic. And these days, actually, we're really happy when things are NP-complete. They're pretty easy, actually. They're still very hard problems there. But actually, we have these things called SAT solvers. And so when you get into NP, if you're in NP and you're NP-complete, that's not a bad place to be these days. But if you add quantifiers to the logic, you get quantified Boolean formulas. Oops, you get your p-space complete. EPR, I can't even remember, effectively propositional, something like that. I can't even remember. It's another logic which I think maybe adds uninterpreted functions to the mix, and it gets harder. Then you get to first order logic, which is semi-decidable. So now we get into the really interesting area. And then you add something like linear integer arithmetic to first order logic, and you're undecidable. And so this is the space where actually most of the fun is, where you've got Turing completeness, you've got undecidable problems. You want to take a program and say, does it ever divide by 0? And for most reasonable programming languages that are expressive enough, that's really hard. So the good part is we can classify these problems and we can say where our problems end up in this space. But actually, often the problems that arise in practice aren't randomly generated. They come from human artifacts and human design. And so it turns out that logic isn't only the basis for describing the complexity classes and thinking about the hardness or undecidability of problems, but in fact, we can give logic formulas to engines in these different classes and have the engines work on these formulas directly to answer questions about these formula. So the most classic sort of things we ask about a formula are validity or dually satisfiability. So here's a formula where, let's say, the variables x and y are real valued, and there's a Boolean connective. So we have two formula, and we might give this formula, as you'll see in a demo later, to an automated theorem prover and say, are there values of x and y such as if I substitute them into the formula and reduce, I'll get true. And a decent automated theorem prover that knows about the reals will come back and say SAT, but better than that, it'll provide you a witness that says, here are some values to plug in so you can independently validate that my reasoning was, the engine's reasoning was correct. So essentially we call these solutions or models. And the idea then is that I have some representation of the formula, I give it to the theorem prover. In the satisfiable case, it comes back and gives us a model. I might change the formula a little bit here and require that x times y is greater than 1 and that x squared plus y squared is less than 1. In this case, we hope that an automated theorem prover in this theory would come back and say unsat. Now in the unsatisfiable case, that is, there's no values of x and y that make the formula true. What else can the theorem provers give us? Well, it can give us a proof, and actually we'll talk about that a little bit later. So in the old days, theorem provers, basically we could think of them as giving Boolean answers. These days it's very nice for the theorem provers to give us additional evidence. So in the case of satisfying assignments, models, and in the case of unsatisfiable result, a proof of why, a proof in maybe a resolution style of the unsatisfiability. And that can be used, again, to independently check the result of the theorem prover, because often these theorem provers, like the one I'm going to tell you about, are written in hundreds of thousands of lines of C++. You might wonder about the correctness of that code as well. Okay, so our theorem prover that's been developed by Leo and Nikolai over the last 5 years is called Z3. And it started out as something called satisfiability-modulo-theories, which basically combined the famous DPLL search procedure for SAT with other theories for dealing with, say, arithmetic. But over time, actually, Z3 collected a lot of other engines that are not generally thought of as being inside satisfiability-modulo-theories. So often you have formulas, you have these terms, and you want to simplify them to some normal form if it exists. There's other ways of doing proof by things like superposition resolution. For other types of queries, you want to do things with Grosvenor bases. So Z3 properly is really a collection of automated theorem provers or symbolic reasoning engines. As I'll show you, I'll give you a quick demo. You can learn about Z3 various ways. There's a lot of papers that they've written about the decision procedures inside Z3, but it's available via a web interface that I'll demonstrate. And also very recently, just about 2 weeks ago, we made the source code available for research and academic use. So all some 300,000 lines of C++ are available out there. It is under active development. So Leo and Nikolai, Christoph Wintersteiger, the main contributors, they are very active, they're responsive. So if you have queries about it, if you want to start using it for your own research, they're happy to help out. Let me just stop here for a second and do a quick demo of what Z3 is like. Okay. All right, so here's a little web browser. You can do this from your iPad or Linux or wherever you like. It's just a web interface to our web server. And on the left-hand side, it shows you some examples. Can you see that all right? Yeah. So here what we've done is, so Z3 is a C++ program. It's essentially a library, but we've created a Python interface by which you can interface with it more directly. So here in Python, we have a bunch of helper functions. Essentially in lines 1 and 2, what we're saying to Z3 is, please create some names, X and Y, that represent integer values. And now please solve this system of simultaneous equations. So we want to find assignments to X and Y such that X is greater than 2, Y is less than 10, and X plus 2Y is equal to 7. Now, this looks like Python code, but what's going on underneath Python has operator overloading just like C++. So what's going on here is we're actually building a Z3 data type, an expression tree that represents this formula. And then when we solve it, we're asking Z3, and essentially the theory of linear integer arithmetic and Boolean combinations to find us a satisfying assignment. So here at the bottom, we see it comes back with an assignment. Y is equal to 0 and X is equal to 7. To show you that it's, it's really live, let's go in there and edit that and say, how about X less than 7? We can ask it again, sends the formula off, and comes back with another assignment. Okay, so that's basically simple satisfiability model generation. Z3 has the simplification capability that I told you about. Here's a bunch of formulas. And Z3, we're asking it to just simplify, so we send that off to Z3, and X plus Y plus 2X plus 3 gets simplified to this expression, and that's just the simplifier, so you can just use that. You're not doing any satisfiability queries. Later in the talk, I'll talk about I'll tell you about the new decision procedure for nonlinear arithmetic over the reals, and here's the example of that. So here now we say to Z3, give us some real variables, and now here's a system of nonlinear equations over those reals, and Z3 comes back, and this is fully precise, infinite precision results in this model generation. So no approximation going on here. The tutorial goes on and on. Z3 has a lot of theories. If you have problems, pure SAT problems, you can do SAT problems. Z3 has a tactic sort of language where you can combine different strategies together. You can script against it now very easily in Python. It has arithmetic. It has machine arithmetic, so it supports bit vector. This is very nice for tools that are doing automated test generation from things like x86. x86 code. You can represent functions, maps. It has some algebraic data types. There's a lot to say about Z3. You can get more of that in the tutorial. Okay, I mentioned a few of the applications. At Microsoft, we're using this Z3 and 5 spaces, so we're building tools on top of this that are doing functional verification in the classic style of a programmer comes up with pre and post conditions for a function. We have ways and loop invariants for their loops. We have a way to encode those in logic and use the Z3 to discharge the proof obligations. A lot of the tools like SLAM and other tools for defect detection rely on Z3 for reasoning about semantics of programs. Test generation is also a big topic. Tools like CLE, if you've heard about them, or SAGE, that explore a path at a time and generate new inputs to try to cover new paths in your program. Essentially, those are satisfiability queries. They're essentially saying, does there exist an input that goes down some previously executed path to some point and then vectors off into some uncovered code and increase your code coverage? Another thing that we've done classically at Microsoft Research, but it's maybe not as well known, is really a model-based design. So if we have higher level languages or higher level models for describing systems, we can explore through synthesis and other things like symbolic model checking the design space of these higher level systems that might be described, say, in a data log or maybe state machine notations. So we have a tool called Formula for doing design space exploration. And then we have new programming languages. A lot of programming languages, their type systems can be enriched by using the theorem prover to say, okay, do I have a list of integers? Do I have a list of even integers, prime integers? Prime might be a little difficult, but you can refine your type system by adding logic, by adding predicates that are over the values in your types. And you can use automated theorem provers like Z3 to actually function as enhanced type checkers. So there are languages like F star from Microsoft Research and other ones which are using now Z3 as part of the type checking process. So Z3 is used by many research groups. There's a lot of downloads. Now the source code's available. It's been sort of #1 in the SMT competition in most categories for a number of years. And this is just to recap sort of the main areas where we use Z3 inside Microsoft. So these are all tools that are basically compiling their formalisms into formula, into logic formulas. So SLAM is using Z3 for doing this idea of predicate abstraction and refinement. PEX and SAGE are these test generation tools. Formula is this design space exploration, and F star is this new programming language. Essentially, it's F sharp with refinement types. So you have the ability to add predicates to your types that describe more precisely the types. And then VCC is our verifying C compiler. It supports C enhanced with contracts, pre and post conditions, and variants. And it uses the Boogie, a verification condition generator, on top of Z3. So we have whole tool chains that have been built over really over almost a decade now, that previously, before we had Z3, targeted things like simplify, but now exclusively use Z3. So these tools generate lots of benchmarks. Through these benchmarks, we enhance Z3 and optimize it. Okay, so that's sort of the background. Automated theorem proving is great. The last decade, we've really seen that the advances in algorithms, as well as the power of machines, have taken it from sort of more of a cottage industry used in certain types of formal methods to really being a tool, a library an engine that powers many, many different tools. So today I want to go beyond what Z3 is and talk a little bit about new directions. So one direction Ken McMillan is pushing on, which is this idea of interpolance, which helps us actually be more precise in our program analysis. The other direction is really thinking about new theories. So these days, a lot of people are concerned about things like cross-site scripting attacks and analyzing programs whose output is a string composed of many other strings. And if you think of like websites, with where you're taking input from the user, input from databases, and creating an HTML page or JavaScript, you're essentially in the world of strings. So can we reason about strings? And as I sort of hinted at with the demo, we have some new take on how to do nonlinear arithmetic. So I hope to get to all three topics. And with these, as we get these new features into Z3, there's a bunch of new applications that these are driving. Okay, so for those of you who are in verification, apologies, you probably heard about interpolation from Ken McMillan many times, but for audience who hasn't seen it, hopefully this will be something new. And here's a pretty high-level introduction to the idea of an interpolation. So, suppose we have Bob who's building data centers and Alice who's building servers for data centers. And Bob has some constraints on the data centers that he's going to build. Let's say M is some measure of horsepower MIPS or something silly. These are totally made up. And he only wants to build data centers that are greater than whatever 10,000 units of this capacity. He has a secret cooling system that if it's turned on, you can go up to 2,000 watts. And if you don't install the cooling system, you can only go up to 1,000 watts. So C is a Boolean variable. It's sort of private to him. He's got this thing. He can either add it or not have it there. On the other side, Alice has got a whole bunch of secret constraints involving how she puts together these machines. Now, some of the constraints actually mention variables that are shared with Bob, mainly this notion of horsepower and watts, right? So we can imagine a situation where Bob sends Alice his constraints, and Alice takes those constraints and conjoins them with the constraints that define the space of the system she's willing to build. And unfortunately, no contract can be signed because these two constraints put together are unsatisfiable. So this actually is not so unreasonable. There are lots of complexity in building products, and you can actually use constraint systems to describe these. To describe the space, the design space of each, or the solution space. And so how would you explain the problem to Bob? Well, we want to do it in a way that doesn't give away all the secrets, right? And interpolation is an interesting idea that came in 1957 from a fellow named Craig that helps us explain the reason for unsatisfiability for certain types of theories. So the setting, slightly more formally, is we have this A formula over some theory, let's say linear integer arithmetic, maybe Boolean formulas, propositional structure, and we have this other B formula, and we conjoin them, and the result is unset. Now, as I said before, a theorem prover, a resolution-based theorem prover like Z3, that proves from A and B, you can derive false, therefore unset, will have a way of representing that proof. And that proof has a huge amount of structure in it, and you can imagine it has in it all the variables that include Alice's secrets and Bob's secrets and the shared variables. So what's an interpolant? So interpolant is a new formula, and it has an interesting property. So the first thing about I is that it's implied by A. So it's a weakening of A, right? It admits more models. Right? If we think of it in terms of satisfying assignments, at least as many models as A and more. It only mentions the variables that are common to B and A, which are by definition M and W, and also that it preserves the unsatisfiability. So I conjoined with B is still unset. So you can just look at that briefly and sort of see that that is the case for this little example. So really what the interpolant is doing is it's a simplified version of A, in some sense, that is explaining the failure in terms of the known common variables. Okay, so that's what's going on. The way Ken also talks about this is if you think of different explanations for why A and B is unsatisfiable, A is one such an, A is a possible candidate, but it mentions a lot of these secret variables. It has a lot, it's very complex. So really what we're looking for here is some generalization of A that doesn't mention all the secret private variables of A, that is weaker, but is still sort of unsatisfiable when conjoined with B. Okay, so just to say this again with maybe slightly more formalism via Venn diagram, an interpolating theorem prover you'll give it a formula that's divided into two parts, A and B, and then the theorem prover will do a satisfiability query on A conjoined with B. If it proves unsat, then it's going to create now, it's not going to give you the full proof, it's going to create this new formula which is an interpolant I, and I has three properties. Okay, so I is implied by A, that's the first thing. So in the Venn diagram it emits more models, right, it's weaker. When it's conjoined with B it's still false, so it doesn't, the red bubble doesn't intersect with the B bubble. Right? And the third, and perhaps, well, all of these are important, but the third important point is that the variables that appear in the formula I are in the intersection of the languages of A and B. So they can only mention the common terms. Okay? So that's sort of the idea of the interpolant. And it turns out for many logics, you have an interpolation theorem which says these interpolations exist. Furthermore, for certain types of logics, they can be derived in linear time from the proof of unsatisfiability. And so an interpolating theorem prover is one that, like Ken has created. So what are these things good for? Okay, so it turns out that interpolants are really useful in verification for simplifying complex proofs using small formulas. So if you think of things like model checking, and we're asking queries about programs, what we're doing is we're creating essentially formulas that represent, say, the reachable states of a system. And these formulas are getting bigger and bigger over time. So over time, we're going to get formulas that are so big they can't fit in the memory of the computer, then Z3 doesn't have a chance. So if there's anything we can do to simplify the formulas, make them smaller, and also focus them on sort of parts that are relevant to, say, a proof we're trying to do, that's good. So interpolants give us a way to do this. And what I'll show you here is just a small example. And then I'll talk about how we use it in practice to scale up interprocedural program analysis. So here we have a really simple program with three statements, and I used a Pascal-style notation here to distinguish assignment statements from equality and logic. So the first statement says x gets the value of y. The second statement increments y by 1, and the third statement you might not have seen. Think of it as a guard, and it says I only let control pass through from this point to this point whenever x is equal to y. And if x is not equal to y, then execution stops. Okay, so I think you can probably see no matter what values you choose for x and y, say these are integer variables, whatever pair of values you pick for x and y, you're not going to get through to the end, right? If you start at the beginning bubble, you set x to the value of y, you increment y, you're not going to get past the guard. But how do we prove that automatically? So Floyd-Hoare proofs are a style of proof that will let us reduce global analysis problems into global verification problems into a set of simple steps that we can discharge with the theorem prover automatically. So the first step here is to reduce the problem to logic, because what I said at the beginning is we have these logic engines. Oh, that's Windows 8 doing some magic for us. Let's see, how do I get back to my slideshow? Oh, yeah. Alt-tab, something, there we go. Okay, so the first thing we do is something known as static single assignment form. And the idea is very simple. Let's call the initial values of x and y, let's give names to values, right? Variables are very problematic. Variables are very problematic because their values change. In logic, we don't have things called variables, we really have just symbols. So let's use the symbols x0 and y0 to talk about the values of x and y at the initial bubble, at the initial state. And whenever we assign in the program over here to a variable, we're going to give it a new name, because that essentially potentially represents a new value. So this assignment statement gets transformed into an inequality that says x1 is equal to y0, right? So x1, the second value of y is essentially equal to the initial value the second value of x, x1, is equal to the initial value of y. When we increment y by 1 here, we say y1 is equal to y0 plus 1. Right? If we just translated without the subscripts, we'd have this logically false statement that said y is equal to y plus 1, which often trips up a lot of people when they see C programs initially. You know, what does it mean, this statement y equals y plus 1? But in logic, y1 equal y0 plus 1 is a more interesting statement. And then the assume is referring to the second values of x and y, so that's going to be translated to just x1 equal y1, right? And now you can see that essentially we might just pose a satisfiability query to the theorem prover, and the satisfiability query would be, does there exist x0 and y0 such that the conjunction of those three formulas is satisfiable? And that's essentially asking, you know, can we get to the end? And you can sort of work that out and see that you can't find such pair of values. So we argued that sort of informally before, but you could now formalize this in this translation, give this to the theorem prover, and get back unsat. Now, you might be thinking, ooh, unsat, I know something, unsat and interpolations. Interpolations can be useful for decomposing the proof of unsat. So how do we think about this program in interpolation? Well, we think of now splitting that formula, that conjunction of those three subformulas into A and B parts. So let's look at the first part. So in the first decomposition, the A part is the conjunction of those two formulas, and the B part is just x1 equal y1. So now remembering back a few slides, what is an interpolant? So an interpolant has to be implied by A, its conjunction with B is unsatisfiable, and it can only mention the common variables. And what are the common variables? That's x1 and y1, right? So the interpolant can't mention y0 because that's only in the A side. So quiz, so okay, what's a potential interpolant we can put there? Oh, I thought I heard something. Yes? Professors can answer too. That's fine.
5 and 4.
I'm sorry?
You want integers?
Oh, you want to give me concrete values.
I'm not going to give you a proof.
Huh? Well, an interpolant's not a proof, right? No, I'm not asking for the proof. I'll give you the proof later. Okay, so anybody? Usually, oops, sorry, I didn't want to give you that one. Yes? You didn't see that.
I was going to say y1 equals x1 plus 1.
Ah, very good. So you're just doing elimination, right? Yes, if you want to get rid of y0, you know the theory of linear integer arithmetic admits quantifier elimination. So you've eliminated y0 by substituting, because x1 is equal to y0, you can substitute x1 for y0 and y1 equal y0 plus 1. You get y1 equal x1 plus 1. Excellent. That's implied by A. It's unsatisfiable when conjoined with B, and it only mentions x1 and y1. Right, so here's another interpolant. And I like this interpolant a little better, because suppose that increment of y is in a loop. Your interpolant's only good for sort of one iteration. Right? This one might be good for an arbitrary number of iterations, right? Because it's a little more general. It's actually implied by your interpolant. So the space of interpolants admits many feasible interpolations. And the point of this interpolant is not just that it meets sort of the requirements of the formal definition, but to say that it has sort of a bias, an inductive bias, where if you imagine the second statement being iterated many times, this interpolant will generalize to other proofs. So anyway, so interpolants, the point of this slide is to just say there's many different types of interpolants, and that it admits a space where you can select. For different theories, you might feel that certain interpolants are better than others. Maybe in linear integer arithmetic with inequalities, you like this one better. Okay, so what do you do with the interpolants at the end? These interpolants are essentially these things that explain the unsatisfiability. It turns out that what Ken has showed is that once you have these interpolants in hand, they actually help you form a proof. So if we think about what we've done, we've gone to this second we've gone to the second column and generated these interpolants. Now what we can do is we can go back to the program and we can construct this Floyd-Horst-style proof. And so what does this proof say? It has basically 3 steps. It first says if you start in any state, so true means all states, and you execute x gets y, you'll end in a state where x is equal to y. Okay, and where did that interpolant come from? Actually, I skipped that part. That was for the different division of A and B, and really the only interesting interpolant at that point is the A part itself, right? Okay, so that proof triple, which said you start in any state, you execute x gets y, you'll get into a state where x is equal to y. You get that post state by taking that interpolant and getting rid of the subscripts. And now if you start from that state, any state satisfying x equal y, and increment y, you end up in a state where y is greater than x. If you start in a state where y is greater than x, and you try to assume x equal y, you'll get blocked. So you'll end up in no state at the end. So essentially that proof of unsatisfiability that I couldn't get from the beginning to the end has been decomposed into 3 steps. It's been partitioned into simpler steps, and that's sort of very fundamental in program analysis. We'd like to do that, and here's an example of a much larger context where essentially we are trying to do a proof. We're trying to do a proof of a big program now, not a program with 3 statements. This program has a main procedure. This main procedure calls other procedures. And what we're doing is we're creating a formula that represents the unrolling or the inlining of this procedure. So you can imagine now this formula is pretty big. And what we've maybe perhaps got is a proof that I can't get through main to an error state going through P and coming to the end. And so my formula, the A and the B parts are as follows. I have my main context around the call to P. Let me try to pretty this picture up a little bit. So the green bubbles, they represent the A part. This is sort of the context around which P is called. And now this yellow part represents my B formula. And essentially what we're doing with interpolation is we're trying to explain why an error can't occur whenever execution goes through P. P is a formula which has many local variables. P is unwound with calls to other procedures. And what we'd like to do is replace this whole subgraph here by our I, which is essentially an explanation of why in this context A, calling P can't lead to the error, right? So interpolation is a way to really, in interprocedural analysis, summarize very complex behavior with hopefully a smaller formula. And so Ken has been working on this idea of getting these speculated summaries from interpolants. And it turns out that in a set of benchmarks using a previous tool called Yogi, these are a set of benchmarks on device drivers. Yogi is a successor of the SLAM tool. Each benchmark here in the x-axis represents the time to complete for the Yogi tool. So this example, and these are log plots. So essentially, each crosshair here represents a run. The x-axis is the time for Yogi, this tool with interprocedural unwinding without interpolants. The y-axis represents the runtime with the duality interpolation. And what you can see here is that we're getting well below that duality is speeding up the verification process essentially by an order of magnitude in most cases. So for example here, we have Yogi runtime in seconds close to 100, duality is under a second. So this notion of interpolation is a really huge idea of simplifying the explanations for unsatisfiability. It's not just an interesting theory from 1957. We put it into the theorem prover, and it gives us the ability to analyze examples in much shorter amount of time. Okay, so questions about interpolants?
You said there were theories for which interpolants were cool. Does that mean that for every pair of statements that the conjunction would lead to having an interpolant existing. I'm asking.
There are theories there are logics that don't admit interpolation.
But
So
those that do, does it hold for all?
pairing. Oh yes, yes, it's universal result within that. Yeah. So if it's unsat, then you can get from the proof structure in various sort of proof formalisms, you can get interpolants generally.
Because the part that's surprising is sort of the secret part, right? That the fact that somehow you can always just use the variables in common.
Right, but how you eliminate them? I mean, it's if your logic admits quantifier elimination, then you have a way to get interpolants, right?
Do the interpolants get small enough for people to understand them?
Oh yeah, actually, Ken had an intern this summer, and he did the interpolation in a new way, which will be published hopefully soon, and he compared it to some other results that we're trying to simplify and get interpolants. And yeah, you know, we have examples where, you know, there's sort of a formula that's sort of 2 pages of text, and the interpolant is like on 1 line. So it's really, you know, in certain cases it's remarkable, the simplification. So, you know, when we want to actually debug systems, if we have especially verification systems, this could be it could be actually usable by humans, in the sense of these things could be reduce things that are unreadable to readable. But again, it really depends on what we're trying to prove and the properties. Other questions? Okay, now for our second part. This is the use of automated theorem provers for something everybody should know, automata theory. So, right, we teach it here. You learn about finite automata, non-deterministic, minimization. You learn about the pumping lemma and the correspondence of finite automata to regular expressions. What's new there? This is like decades old. We have all the algorithms. They're all encoded in JavaScript. I mean, every library implements something. Okay, so the idea of symbolic automata is, can you take all the classical results from automata theory and extend those results, the theoretic results and algorithms, to work modulo large, very, very large, maybe very infinite, countably infinite alphabets. So imagine, you know, you have an alphabet with 5 symbols, right? That's great. But imagine, like, you know, you want to do regular expressions of a Unicode. I don't remember Unicode, but it's a little bigger than ASCII. And then, you know, imagine you want to do, your alphabet is bit vectors of 32 bits. So there's, or 64, right? How would you do this with classic automata? Well, it turns out for most of the algorithms, the big O complexity is linear in the size of the alphabet generally. There's a linear factor. So if your alphabet's really large, classic algorithms are just going to, even if this number of states is small, classic algorithms will have this problem. And so what Margus Vianis has been doing with Nikolai Bjorna is revisiting formal language theory from the viewpoint of the notion of making things symbolic, using things like Z3. And there's a whole, you know, interesting set of results around word acceptors. So we have classical word acceptors, non-deterministic finite automata. We have I/O automata, where for every input symbol you read from a tape, you output a single symbol. We have these things called transducers, which actually can output a string for every input symbol read. These create a hierarchy of automata. And actually what Margus and Nikolai have shown is that, yes, indeed, you can lift classic algorithms, it's not trivial, to symbolic word automata, acceptors, and transducers. So this means you can now do regex matching with really large, even if infinite alphabets, and you can do certain classes of transducers as well. And so these are results over the last 3 years. Most recently, you can read about symbolic transducers in Popple. So here's the very basic idea. What we're keeping finite is the states. So we're still going to have a finite set of states. So let's say here's a very simple state machine with 2 states, P and Q. But what we're going to make symbolic are the transitions. So in a classic, say, transducer, you might have a lot of transitions that look of this form. You know, here's a symbol. On this symbol, this escaped x80. If you see that on the input side, then on the output side, create a string with these 2 symbols. And that's a single transition. So it says, you go from P to Q if you see in the input tape the symbol before the slash mark, and you output the string of symbols after. And so there might be a lot of those transitions on the left-hand side. For a large alphabet, you might want to go from P to Q on many transitions. And if you have to explicitly represent each of those, it might be large, say thousands. And we do see that in practice. So what's a symbolic transducer look like? It looks like a little program. And it really looks just like logic is what it looks like. So it has two parts. Let me try to get my color here. Nicer. Okay, so the first part is essentially a guard. It's a little lambda expression, but don't be scared about lambdas. You should have all seen that, I think. So lambda x, it says if the x symbol satisfies this predicate, and what is this predicate? It's just a predicate in the theory of bit vectors that says x is greater than or equal to this 16-bit, this base 16 number, and less than or equal to this 16-bit number. Okay, so that's the guard. It says only transition from P to Q when that's true, and then the output is just a bit vector expression that has conjunction, bitwise concatenation, bit extraction. So here we're extracting some lower order bits of x, some higher order bits, I guess, and so really it's a little program. Right? And so the point here is if we enumerated all the values of x for which the guard is satisfied, then we would get the 1920 transitions on the left-hand side. So one way to compile a symbolic transition is to just compile it into the explicit state representation, but then we get a blow-up. So the question is, can you reason, not only can you, we know we can represent automata this way, but can you reason with them? And the answer is essentially yes. So imagine, you want to know, is it possible to compose two edges together with the two guards? That is, if I have one guard and then I want to know if that guard is met, can I go to the next edge? Often in automata we want to compress transitions for minimization. So if you wanted to do that explicitly, you'd have sort of a cross product operation, right? But with symbolic, you have just really sort of an implication test, essentially, some sort of containment test or conjunction. And so the point is they figured out ways to take the classic algorithms and sort of the operations on edges now can be done directly with formulas. And these formulas are very compact encodings of large sets of edges, right? So for most of the cases, the big O complexity of these symbolic algorithms matches that of the classical algorithms with a factor for the decision procedure. So it turns out that these algorithms are a big win when you have large alphabets because the symbolic representation is smaller, but it turns out also the call to the decision procedure is much cheaper than sort of doing the expansion to the explicit case and enumerating. For small alphabets, this is not a win. So it's not to say that we have algorithms that are, that improve the big O complexity. They're about the same, but for state machines with large numbers of transitions, the symbolic approach is a win. So here's an example sort of the sort of analysis we can do now that we have symbolic word acceptors and symbolic transducers. The nice part about these things is they're closer to programs, right? Because they have program-like expressions in them. So one of the things we might want to do is say, oh, I have a function in some domain-specific language for doing transduction. And I'm going to do UTF-8 encoding of strings. And I have a regular expression that represents the set of UTF-8 strings. And I want to know, is that function correct? So this is a verification question that in general is difficult for arbitrary programs. So I want to know, is there an X such that if I UTF-8 encode it, I end up outside of the set of desired regular expressions. So with symbolic automata, we have a library built on top of Z3 that lets you answer this question quite directly. First, we can take a function in a restricted language and we can create its symbolic finite state transducer. Let's call that E. We can take the regular expression and compile it to symbolic finite automata and complement it. Let's call that A. Then we can do composition of the transducer with the acceptor. The result of that is a set B, and we ask, is B empty? Okay, so let me do a quick demo of what that looks like. Again, we have a little We have a little website here. So for symbolic automata, you might want to know, how do we write a symbolic automata? So at the library level, we have an API and a data structure. At the program level, we have a language called Beck, which is slightly C-like, sort of JavaScript-y. It actually has variables. It has pattern matching. It does the transduction by yielding characters. And so you can see here, it's iterating over everything in the input. It's doing a case analysis on the input, it's yielding characters. And what I can do is I can, in this script, I can actually encode what you saw in the PowerPoint directly. So I can say, take that program, explore it, which means create a symbolic finite state transducer. Now take the regular expression representing UTF-8, which is that thing, believe it or not. Create a regular expression, complement it, do the inverse image, call that B, ask if B is empty. So these are just sort of classic questions we can ask of the library. And whoops, let's see, is it working? Did I press the button? Oh, yes, I did. Okay, so something came back, and here's what it said. It said result subset relation is false. So it actually found it, and it found a string which is actually incorrect, that demonstrates that the function is incorrect. So it says, here's a counterexample where B contains a string, and the reason that that program is in error is that Margus seeded an error here. Maybe you saw that. Fix to uncomment, ask it again. It comes back and says subset relation is true. Okay, so that's Beck. That's symbolic automata. Symbolic automata is a library. It uses Z3 to essentially reimagine sort of that classic automata algorithms using Z3 to discharge all these queries about the alphabet. And there's papers on it. There's a library, and the websites you can visit here as well. Okay, so that's application number 2. Do I have time for one more?
How long is it?
5 to 10, depending. Okay. First, questions on symbolic automata transducers. Okay, and this stuff is actually getting used in Microsoft. People, this idea of sanitizing, for websites, you take JavaScript in, you want to make sure that you don't have cross-site scripting attacks, or you, like Facebook JavaScript, you want to rewrite the JavaScript in some way, and you want to know that the rewritten code has some property. Yeah?
What about using formulas for describing states?
Oh, yes, very interesting. So the question is, can we generalize in a second dimension? Can I describe my set of states using formulas too? So now you're like stepping into dangerous water. I don't know. Answer is I don't know, because now you're describing maybe not a finite state automata. You're describing some other type of automata. The answer is I don't know. We haven't looked at that. We have pushed out to push-down systems. So you can look at other types of language formalisms. But that's a very interesting question. You might come up with some sort of formalisms where for certain types of logic you can also represent the states symbolically. But yeah, we haven't done that. Good question. Okay, last part. Fun stuff. Okay, so polynomial constraints. So what I showed you before in the demo, the fancy word is the existential theory of the reals. Basically what that means is I have a system of equations with real valued variables. The coefficients can be reals as well. And I have inequalities, I have a conjunction, it's nonlinear, so I have x squared, x cubed. How do I do solving in this sort of system? So this is, polynomials go way back. There's a nice history here. I'm not going to go through all the people here, but maybe you might know who some of them are. I think that's Gauss, Newton. Galois, no, that's Gauss. Who was that? That's Descartes. Yeah, Descartes, And then, okay, so what happened in this history of people investigating quadratics and polynomials? Well, eventually Tarski sort of said, hey, things are decidable. That is, the real closed field admits quantifier elimination. But the only little issue with his decision procedure was it had non-elementary complexity. So, you know, that's a tower of exponentials whose height is some parameter of the input size. So, not very realistic. Then in the 70s, Collins came along and said, ooh, I have a way to decompose the problem, and now it's only doubly exponential. So actually, this is, to this day, sort of the effective algorithm. Okay, and I'll give you an idea why it's doubly exponential, and I also want to say, we are not bringing down the big O, we are not bringing down the complexity. What I'm going to show you is sort of that we have new heuristics from from SMT solvers, from satisfiability-modulo-theories, that we've used to improve CAD in some interesting ways. Okay, so there are lots of applications for this theory that are generally outside of program verification and testing. Here's just some pictures of things like doing simulation of airflow, you know, plotting. I was talking with somebody earlier today about, you know, you have all these airplanes going through the system, and yeah, Zonomir, right, thank you. And you don't want them to collide. How do you model that? Dynamic geometry systems, you need to solve these sort of things. Electric circuits. If you can solve bigger systems with more variables, all the better. You can do bigger science, right? So many applications here. So going back to logic and complexity, how hard is the existential theory of the reals? Well, it's easy to show it's NP hard. So you have a real value. Let's say you have a SAT formula and you want to get your polynomial system. You say, oh, I'm going to treat a real value x as Boolean by adding an equation that constrains x times x minus 1 to be equal to 0. So I have a choice of two values, and then if I have a clause, x or y or z, I'm going to essentially say, oh, x plus y plus z should be greater than 0, right? And so it's NP hard pretty easily, and in 1988 by separate folks it was proved to be in p-space, but there's no precise characterization, so it's still good for a PhD thesis. Okay. So here's the big picture of how CAD works, and then I'll vary this. CAD is quite complex, so I am reducing it. This isn't even a 30,000 foot view. It's like the view from Curiosity on Mars, back to Earth. Okay, it's really fast and loose. So apologies to people who do know cylindrical algebraic decomposition. We have this system of equations. The first step is to get rid of variables because multivariate inequality is hard. So various things happen, projection and saturation operations, and you get a bunch of new polynomials. And what's the size of that set? Well, in the worst case, it's exponential in the number of equations you started with. So that's sort of hand wavy how you get your first exponential. But this is just a space blow up, space and time. You haven't even started to search. The next thing is we want to find satisfying assignments for x and y. Okay, so here's one of the beautiful ideas in cylindrical algebraic decomposition. Well, the reals are really hard to search over, right? Because they're not even countable, right? You know, you try to count them and more slip in. So doing search over them seems infeasible, but what cylindrical algebraic decomposition says is for every polynomial of a certain form, there's this decomposition into finite intervals such that the sign of the polynomial is the same for whatever value you pick within the interval. And that's because polynomials have nice continuous behavior, and you find these feasible cells or these decompositions by looking at derivatives and doing fancy things that I won't describe. Okay, so once you have this finite decomposition, you can do search, because search is all about, you know, taking this finite space and probing it. So you might pick out, let's a value for x like -2 and substitute it into the original equations. Now you get a bunch of simplified equations, and here, for example, the first equation that we have, x squared plus y squared minus 1 less than 0, it simplifies to this, and we do this. And this is nice because it doesn't have x anymore, and here are the cells for the decomposition. But notice that that polynomial, that reduced polynomial, is positive in every cell. Oops, we wanted it to be less than 0. So that assignment to x was a bad choice, and now we have to backtrack. So the search means, we're going to make guesses, and we're going to go down some place trying to find, making deductions based on the search, based on the model, and then we're going to have to backtrack. So that's sort of the second exponential. Okay. So what do? We take CAD, and we add a lot of the learning from sat solvers and many of the tricks. So the first idea is don't take a hit, an exponential hit in space and time in the start. Like, start searching immediately without doing the saturation, because the saturation is not being guided by the model. What you want to do is you want to be smart. You want to sort of say, after I make this assignment, then what should I saturate? What should I project? And so the first thing we do is reverse the process, and that's non-trivial to figure out how to do that. The other aspect is there's lots of things that sat solvers do that help cut down the search space. One idea is non-chronological backtracking, which means, like, when I get a conflict, I don't have to just go back one step. I can figure out how to go back many steps. I'll show you that. And the other is lemma learning. So, like, when I get a conflict, when I get to some place in the search space where I'm stuck, I don't want to repeat that mistake over and over again, right? I want to learn some new fact from my failure to find a satisfying assignment and do that. So here's one idea. How do you use the solution to guide the search? So suppose you have three polynomials, right? Here, here, and here. We have this orange one, and they're described by these curves, and we have these two blue ones. And we've essentially got a feasible region, which is the intersection, of those three spaces. And so now the search procedure doesn't know about that space. It's trying to see whether it's non-empty. There are points. And it chooses x equal to 0.5, which is outside the space, right? And now what it tries to do is extend it to y, right? And so it turns out that these two polynomials on the left are sufficient to show why you can't extend, if you chose x to 0.5, why you can't extend y anywhere, there's no y. And so it turns out that when you get that knowledge that these two formulas are sort of at the root of the conflict, then you want to sort of do projection and saturation and sort of figure out some other formulas. But look at this formula over here. It's sort of sitting over there. It turns out you don't need it. Sort of once you've sort of figured out that these two formulas sort of describe the conflict, you don't need to do saturation necessarily yet on this other one. So whereas in CAD, traditionally, all the formulas get saturated without knowledge of the model, here the saturation is going to be guided by knowledge about the conflicts and about where the feasible regions are for subsets of the formulas. Okay. So the other idea, which is very simple from sat solving, is the grasp algorithm known as the grasp non-chronological backtracking. So suppose you have this constraint, x times w is equal to 1. You make some decisions, x is equal to 0, y is the square root of 2. You're going through search, and then you get to w, and you say, ooh, whatever value I choose for w, I'm in conflict, right? I can't get a satisfying assignment. So typically you would backtrack to z and say, let me try z equal 2. And then maybe when I choose w, things will be better. And that's a losing proposition here, right? So in sat solvers, what you do is you sort of do very simple analysis to say, ooh, the relevant variables for the conflict are x and w. And therefore, when I get a conflict here, let me backtrack and try a different value for x, because it's clear that y and z are irrelevant to this conflict. So this is actually a very key part of sat solvers, never been done in CAD. The other thing is lemma learning, and this really gets a little tricky because lemma learning combined with CAD is non-trivial, but here's an example. You have a current assignment, x and y are both 3/4. You have a conflict because no matter what value you pick for z here, you can't satisfy that inequality. Now, if you're backtracking, you might just try some other values for x and y, but there are lots of other values to try. You'd like to basically rule out a whole region of space which is unprofitable to try. So you have one example that creates a conflict. From that, you want to generalize. It's sort of like interpolation in a different way. You want to get the very general explanation. And so Leo and Dayon have come up with a way to learn a lemma that essentially characterizes this space so that you won't pick values x and y outside of that hemisphere, right? So lemma learning is key. And why, all these things are just heuristics. Why does this matter and does it improve things? And I'll show you it really matters and it does improve things. First of all, people say things like, oh, CAD is polynomial for a fixed number of variables. Oh, by the way, CAD works with precise representations of the roots of polynomials called real algebraic numbers, and they can be very expensive to compute with. CAD is essentially polynomial for a fixed number of variables. Yeah, that's R is the fixed number of variables. So you can see, that's as R grows, how big a system are you going to really get to? So the point is, with this sort of search, every detail matters. If you can do things like lemma learning, non-chronological backtracking, you can make big advances. So here's just, let's just concentrate, forget all of the table except these two lines. NLSAT, which is our new prover in Mathematica, and let's just concentrate on Meta-Tarski, which is 1,006 different satisfiability queries. And Mathematica, whose cylindrical algebraic decomposition procedure is over a decade old, okay, solves all 1,006, did I say 106? 1,006 queries in approximately 800 seconds. NLSAT, which is just 1 year old, doesn't quite get 1,006, it gets 1,002 in 343 seconds. So this is a new engine that's very competitive with a decade-old decision procedure for the same logic. We have lots more optimizations to do. And we've compared it to many other solvers that also go after the reals. So I think this is a pretty big advance. I don't know how many variables or equations we're going to be able to go to, but I think it's a nice result in combining learning from the automated theorem proving world of SAT solvers with cylindrical algebraic decomposition. So logic is the calculus of computer science. We use it for formalizing things like complexity theory. We also can compute with it through automating it and using logic engines as a service for many tools. And I've showed you about interpolants, automata, and nonlinear arithmetic. I didn't get a chance. There's also a whole extension to computing fixed points with symbolic methods, but that's for another day. Thank you.
We'll go ahead and take questions.
Have you done any work to automatically translate from traditional programming languages to your automata language?
Oh, yes.
How hard is that?
To the automata language. I thought you were going to say to Z3. So we have something called verification condition generation, which helps you if you're building tools that want to go from programs to formulas. That's called Boogie. And we have a lot of tools that use Boogie as sort of an intermediate representation. So you don't interact directly with Z3, you go through this other layer. Right, so if I wanted to take JavaScript, for example, and translate it to symbolic automata, we have not done that. It's a good question. I mean, essentially in things like SLAM, we did predicate abstraction. There are parts of JavaScript or C that you would hopefully directly encode into symbolic automata, and others you'd have to abstract. So yeah, we haven't done that. It's an interesting question. How you would do that, but yeah, generally, I think we could add procedures to the Beck language, maybe for transducers, for automata, we probably, so we could get closer. With SLAM, we had something called Boolean programs that were very limited. The only variables you had were Booleans, and you could just do propositional calculations. So clearly, it gives a step up, but then C in JavaScript you've got, C you have pointers and you have references in JavaScript, so you still have to sort of get rid of those. You have to compile those away. So there's still a lot of difficult problems.
Questions?
Oh, yeah.
Does Z3 handle any non-classical logics, like separation logic?
No, it does. We haven't gone non-classical, although Josh Burdeen is in Cambridge and he works on separation logic provers where he's doing various tricks outside of Z3 and then generating formulas into Z3. But yeah, no, we don't have like the separating conjunction or things like that. I mean, fundamentally, you can encode some of that and hope that the Z3 quantifier tricks will help out, but that's pretty tough stuff. So yeah, we're not dealing with those exotic forms.
Let me pick up, I think it was David's question earlier about the readability of the interpolants.
Oh yeah, right.
That was, I wasn't looking at that, but it was, yeah. And there's this sort of strange thing happening, right? There's this, none of these things sort of should work if they were just sort of randomly, like if it had no structure.
Oh right, goodness, right. Yeah.
And so why, like, is it reasonable to think that, you know, that a proof like a search-based proof procedure is going to discover elegant lemmas, it's going to discover a small interpolant, right?
Well, I think if the problem has structure, so I think the alignment of interpolation with procedures is a good one, right? Because at the procedure boundary, we know there are local variables that we probably don't want in the interpolant, things that are private to the procedure. And so, you know, classically in logic, we would think of just, you know, in the semantics, if we gave sort of a semantics, we would think of representing those with existential quantifiers, and that would be sort of like our interpolation. So yeah, I think the interpolation works because of a choice of A and B's, right? And so the A and B and the sort of underlying structure define what variables are in common and which are private. And so that decision is up to the creator of the tool, which is sort of this separation, right? And that I think is you know, for the procedure level is sort of key. I think you can't expect it to just give it arbitrary A and B formulas and have nice division. So Ken talks about that as sort of, you know, if you think of procedures with pre and post conditions, those are sort of the natural interfaces at which we describe contracts for procedures. They're also sort of what we use to get the interpolant structure. For other types of systems, where do you get that structure from? Like a finite state system. I don't know, in bounded model checking, what you just do is you just sort of say for each k, I just split the trace before k and, well, for every point I think of time before and time after. So I get a local explanation. But yeah, it's a good question.
When you mentioned Ken McMillan, who's kind of brilliant verification guy. But I remember he was saying, people often think that there's that we write with clean structure, and you mentioned like procedures and there's procedure summaries.
Right.
And Ken was, I think in a bad mood, saying a lot of things only work by accident, right? Right. So let me make this more concrete, less philosophical.
Okay.
Do you see a difference, like if you're trying to verify poorly written code?
Yeah, right.
Okay.
No,
Let's come out worse.
So I mean, our experience with SLAM is just if we have a device driver that's poorly structured, which means generally it has lots of global variables, then our abstraction has lots of global state, and we don't benefit from procedural abstraction. So I think fundamentally, what we've seen in program analysis is that bad programming practice leads to blow up in your state space, right? Because you might have this global variable, but now you can't localize where it's useful necessarily, right? That its scope is global, so where can you eliminate it? Where can you keep it? And that becomes a hard program analysis problem. A local variable in a procedure, when the procedure goes out of scope, local variable's gone. So, fundamentally, we've definitely seen that in SLAM, and I think again, yeah, if you've got spaghetti code with go-tos and lots of global variables, the idea that some mechanism is going to get structure out of that is wishful thinking generally. So.
Have you, for your nonlinear arithmetic, do you work at all with sort of unboundedly long polynomials. I'm thinking of sort of transcendentals.
Oh.
For example, e to the x, where the coefficients are, easily described by a procedure.
Yeah.
You can imagine kind of lazy evaluation.
Yeah.
In your search procedure. So
Right.
you only go out as far as you need to.
Yeah, that's interesting. So it is using some sort of big num package, right? So there is some laziness already in our implementation. Sort of going to transcendentals, yeah, we've discussed that a little bit, but nothing yet. Yeah, that's interesting. Trigonometry, I think, is the next.
Any last questions? One place, one place. Right, thank you.
Great, thanks again.